Okay, so Bronsted-Lowry acids and bases came up a couple slides ago in that table, so now's a good time to define them and to show that it's a broader definition. Anything that's an Arrhenius acid will be a Bronsted-Lowry acid, but not necessarily every Bronsted-Lowry acid will be an Arrhenius acid. So let's look at the difference. According to the Bronsted-Lowry theory, acids donate protons. So in the reaction of hydrochloric acid and water, HCl is the acid because it donates the H+. Water is the base because it accepts the H+. So we see here with the picture, the HCl molecule, which again, if it were in water, it would be dissociated into H+ and Cl-. As it interacts with water, the H pluses go on to form H3O+ with water. One of those lone pairs of water is where the H+ sits, and now it makes the hydronium ion, H3O+, and then what's left behind is the chloride ion, Cl- from HCl. So here we see that the HCl and water, just like when we talked about Arrhenius definition of acids, HCl was an acid in water because it's a source of H+, or in this case, it donates an H+ to water to form H3O+. Now, if we look at Bronsted-Lowry bases, well, again, the bases accept a proton. If you remember, the Arrhenius definition is the bases generate OH- in aqueous solution. Here, accepting a proton is quite different. So you no longer have to have hydroxide involved at all to be a base if you're a proton acceptor. If we look at the reaction of ammonia and water, NH3 ammonia is the base because when we look at the product side, we see that it's NH4+, so it's increased by an H+. So it must have been the proton acceptor. In this case, the water is actually the acid. It's the proton donor, right? When we look from left to right, the water goes from H2O to the OH-, the hydroxide ion. So in this case, we have a base that's both a Bronsted-Lowry base and an Arrhenius base because the ammonia does generate OH- hydroxide ion in water. It is an Arrhenius base, but because the NH3, the lone pair on the nitrogen, is a proton acceptor, it also fits the Bronsted-Lowry definition. Now, what we tend to look at in Bronsted-Lowry definitions is we look at reversible reactions, if you think back to chapter 9. Here we have reversible reactions. These are weak acids and weak bases where it doesn't go completely. They're weak electrolytes. They dissociate and they go to a small extent, but there's not complete dissociation. So in the case of either the reversible reactions or the weak electrolytic behavior, we get a forward and reverse direction. So in any acid-base reaction that we look at in the Bronsted-Lowry sense, we have two conjugate acid-base pairs. So each side is related by the loss and gain of that proton, right? So we're still dealing with the definition of an acid is a proton donor, a base is a proton acceptor, but one will occur in the forward direction and the other occurs in the reverse direction. So as we read that reaction, HA plus B is in equilibrium with A minus plus BH plus. So in the forward direction, the HA is the Bronsted-Lowry acid. In the reverse direction, the A minus is the Bronsted-Lowry base. So whatever served as the acid in one direction, its conjugate is now a base. Likewise, with the B in the forward direction, the B on the reactant side is the neutral base, and on the product side it's BH+, which can serve as an acid in the reverse direction to give up an H+ from BH+ to reform B. So that's our second conjugate acid-base pair. So whatever's an acid in one direction, its conjugate is the base in the other. Whatever's the base in one direction, its conjugate is the acid in the other direction. And again, the H+ is what we're following. All right, if we look at HF, notice when we talked about acids, we didn't quite distinguish between strong and weak acids, but HF is actually a weak acid. The other ones, HCl, HBr, HI, those are all strong acids. HF's a weak acid because it stays mostly as the HF molecule, even in water. A little bit of it will dissociate into H+ and F-, but not completely. It's an equilibrium process, and it doesn't go very much in the forward direction at all. If we look at another conjugate acid-base pair, if we consider that equilibrium process, the HF donating a proton to water to form F- and H3O+, while in the forward direction, the HF is the acid because it's the proton donor. In the reverse direction, the F- is the base because it accepts a proton to reform HF. If we look at the water in the forward direction is the base. It accepts a proton from HF to form H3O-, but in the reverse reaction, the H3O+ donates a proton to the F- to form HF. So the base, the Bronsted-Lowry base H2O in the forward direction, its conjugate H3O plus is the Bronsted-Lowry acid in the reverse direction. So we have conjugate acid-base pairs. If it's an acid on one side, its conjugate is a base on the other. If it's a base on one side, its conjugate is an acid on the other. Now, if we consider the reaction of ammonia with water, if we look at that in Bronsted-Lowry terms, we have the NH3 gas, which gets dissolved in water to form NH4 plus and OH minus. Again, it's an equilibrium process. We see the double arrows there separating reactants and products. That tells us that the reaction goes in both the forward and reverse direction. And honestly, it doesn't go in the forward direction very much at all if it's just ammonia gas and water. So we go a little bit in the forward direction, but mainly the reverse direction is favored, so that we have mostly NH3 molecules and H2O molecules and relatively little NH4 plus and OH minus ions. Okay, if we read this reaction, we say that the ammonia is the base in the forward reaction because it accepts a proton from H2O to form NH4 plus. The H2O is the acid in the forward direction because it donates a proton to form OH minus. If we look at the reverse direction, the NH4 plus is now the proton donor because it donates a proton to OH minus to form H2O, and the OH minus is the base, the proton acceptor, because it accepts that proton from NH4 plus to form H2O. All right, so if it's an acid in the forward direction, its conjugate is a base. If it's a base in the forward direction, its conjugate is an acid. Hopefully that all at least sounds logical by now, but if you don't try it yourself, you'll never know for sure, right? So here's a learning check to look at conjugate base and conjugate acid behavior. Remember, this is Bronsted-Lowry definition, so we're really just following the H+. The conjugate base would be an H+ less than each of those acids. The conjugate acid would be an H+ more than each of those bases. So go ahead, it's not a multiple choice question, right? For A, B, and C in number 1, you're writing the conjugate base of those acids. For A, B, and C in number 2, you're writing the conjugate acid for those bases. Please go ahead and pause the video here and do that now, and then start it back up when you're ready to check your work. All right, hopefully you arrived at all these same answers. So for number 1, the HBr, if we take an H+ away, that leaves us a Br-. Don't forget the plus as well as the H. H2S, that's hydrosulfuric acid, by the way, right? It's because we use the hydro prefix since it's just H and S as elements involved. So the sulfur root, it's hydrosulfuric acid. So people sometimes confuse that with our plain old sulfuric acid. So if we take an H+ away from it, we get HS-. And if we look at the carbonic acid, H2CO3, removing an H+ leaves us HCO3-. All right, hopefully that part went well. The next part where we're taking the conjugate acid of the following bases, well, in the first part we subtracted an H+. Here we're going to add the H+. So if we have NO2- to start, an H+ is going to make HNO2. Notice we're neutral now because we were an anion with a -1. We added a +1 with the H, and that gets us neutral. In the case of B, ammonia, that was neutral to start, so when we add an H+, not only do we go from NH3 to NH4, we also have a plus charge, so we're the ammonium ion NH4+. Finally, OH-, when we gain an H+, becomes H2O. So we've seen that a few times. Hopefully that was an easy one. Hopefully they were all easy ones, honestly, right? And you're doing well. If that's not the case, please do try some additional practice. And if you're still struggling, then certainly reach out to me for guidance. And guess what? You didn't have to wait very long for some extra practice. Here's another learning check. In this learning check, you're going to identify the sets that contain acid-base conjugate pairs. So look at A, B, C, D, E. If they all contain conjugate acid-base pairs, then great, you select them all. If some do and some don't, select the ones that do. And remember, it has to be the acid and its conjugate base, or the base and its conjugate acid, not just anything that could be a conjugate acid or base. They've got to be a pair that goes together, so they should differ only by an H+. So select those, pause the video here while you make your selection, and start back up once I think you've identified all the sets that contain those conjugate acid-base pairs. Okay, so hopefully you identified A, D, and E as the sets that contain acid-base pairs, right? In the case of A, D, and E, we differ just by an H+. Either the first species has an H+ extra than the second, or the second has an H+ extra than the first. B and C, if you looked carefully, B, you were losing 2 H+, and we don't do that. We just lose them one at a time here for conjugate acid-base chemistry. And C, the issue was you were also gaining some oxygens as you lost your H+, right? So that was no good. You had to be just an H+ different, a single H+ different than you started or ended, okay? So hopefully if you did make any mistakes here, you're doing better now. And as I always say, if you're having real trouble and you've tried some extra practice and it's just not making sense, please don't hesitate to contact me for some extra help. Okay, here's another learning check, right? We really want to make sure you have the basics from this first section of chapter 1 before we press on. So in this learning check, you're looking at a given species. It's either a conjugate, it's either an acid or a base, and then you're asked to identify the conjugate of that substance. So in the first one, you're asked for the conjugate base of HCO3-, and you'll select just like on our exams through the multiple choice answer choices. Okay, so please pause the video here while you work on those 4 questions, and once you think you've identified the correct conjugate, please go ahead and start the video back up. Okay, so choice A was correct for number 1. The conjugate base of HCO3- is CO3-2-. We take another H+ away, and the H removes it so that we're just CO3. And since we're already -1, taking another plus charge away makes us a -2. In the case of number 2, C was the correct answer choice. The conjugate acid of HCO3- is H2CO3. So instead of subtracting an H+, as we did with HCO3- in the first question, now we're adding an H+, and we get H2CO3. We'll find that there's something special about a species that can either gain or lose an H+, and we'll call that an amphoteric substance or ampiprotic, and we'll see that buffer systems often use those, like the bicarbonate buffer system in our body, so it resists pH change. 3 and 4 are also a single substance that can either have a conjugate acid or base, and number 3, A was the correct choice because the conjugate base of H2O is OH-. That's an H+ less than H2O. And number 4, C, the conjugate acid of H2O is H3O+, which is just increased by 1 H and 1 plus charge. So I would imagine most of you are getting the hang of this. If you're not in that group, please do some extra problems, check out the homework set, and definitely reach out to me for help if you're still struggling. Okay, with a final learning check before we leave this section of chapter 10, identify the acid-base conjugate pairs for these 3 chemical reactions. So remember, you'll have an acid on one side and its conjugate base on the other, and then you'll have a base on one side and its conjugate acid on the other. And so just identify those pairs for each of these 3 equilibrium processes. Pause the video here. When you're ready to check your work, start back up, and hopefully you'll identify all of those correctly. Okay, so here we are. Hopefully you arrived at the same solution here, the conjugate acid-base pairs for that first reaction. The HI is the acid in the forward direction, and therefore the I- is the conjugate base. The H2O is the base in the forward direction, so the H3O+ is therefore the conjugate acid. For the second reaction, we have HClO is the acid in the forward direction, which means the ClO- ion is its conjugate base. The H2O again is the base in the forward direction, so therefore H3O+ again is its conjugate acid. And finally, for phosphoric acid, H3PO4 in the forward direction, that's our acid. And therefore, in the reverse direction, the H2PO4- is its conjugate base. And yet again, water, good old H2O liquid, is the base in the forward direction, so H3O+ is its conjugate acid. Now, obviously, it's not always true that we have a water acting as the base, but oftentimes it does, and in these 3 examples, it is indeed. So hopefully that works well, and you're getting this. If you're struggling with any of this, or you just would like to see what it looks like with water acting as an acid in the forward direction and another substance being a base, please do check out some end of chapter problems or get in touch with me and I can give you loads of problems if you'd like more practice. Okay, otherwise, if things are going well, and I certainly hope they are, then we'll see you in the next section of chapter 10 when you move on to that.